Okay. Introduction to machine learning with Python. Me and my colleague Irene are going to be taking you through this topic. So machine learning is a field that enables computers to learn from data and identify patterns without explicit programming. Systems improve performance on tasks with increased data exposure and minimal human intervention. Types of machine learning, there's supervised learning and unsupervised learning, whereby supervised learning trains models on labeled datasets to make predictions on unseen data. So these labeled datasets are basically input data mapped onto output data to make predictions on the new incoming data. Under supervised learning, there's regression, which predicts continuous numerical values such as stock or house prices. Then there's classification, predicts categorical labels such as email spam detection and image classification. And then under unsupervised learning, which trains models on unlabeled data to discover patterns and relationships independently. The types are clustering, which groups similar data points based on features such as customer segmentation. Then there's anomaly detection, which identifies unusual or rare observations such as fraud detection or network intrusion. For example, you have a bunch of 50K notes, and then notices that 150K note does not match the rest. It singles that out, hence helping with fraud detection. Then other types of machine learning include semi-supervised learning, reinforcement learning, and self-supervised learning. End-to-end machine learning is a concept in AI where a system learns to perform a specific task without relying on intermediate processing stages. It encompasses the entire machine learning pipeline, including data collection, data cleaning and processing, feature engineering, model selection, model training, model evaluation, hyperparameter tuning, model deployment, and maintenance. Then exploratory data analysis, which is also known as EDA, and feature scaling. So EDA is a visual and statistical exploration of data sets to summarize their characteristics. It is applied during the data preparation phase, focusing on data cleaning and feature engineering. This helps understand variable distributions, relationships, patterns, and anomalies. Then also relevant features are then extracted for data modeling. Feature scaling transforms numerical features to a similar scale, crucial for model performance, therefore preventing one feature from dominating the model due to scale differences. Types of feature scaling, there's standardization and normalization. Standardization, the mean is subtracted and divided by the standard deviation, while normalization scales features to a fixed range, usually 0 to 1. Other types of feature scaling include log scaling and robust scaling. Then I'd like to talk about the concepts of linear and logistic regression, whereby linear regression is a linear model that predicts a continuous output variable based on one or more input features. The equation is given as shown below. Then types include simple linear, multiple linear regression, and multivariate linear regression. The assumptions of linear regressions are linearity, independence, homozydicity, predicting continuous outcomes such as house prices and sales. Then under logistic regression, which is a method for binary classification that models the probability of a binary outcome based on predictor variables. The equation is given, and the assumptions are binary dependent variable, independence of observations, and no multi-collinearity. use cases are predicting binary outcomes, e.g. spam detection and disease presence. Then k-nearest neighbors, which is also KNN, is a supervised machine learning algorithm used for classification and regression that operates on the principle of future similarity to predict outcomes. So you're given a data set and you're supposed to get points, training points from these data sets onto the new data and find the shortest distance using the Euclidean distance metric, which is also, that distance measured is also known as the k-nearest neighbors, which is grouped and then the result is good. Yeah. Other distance metrics used are Manhattan distance and Hamming distance. Weighing schemes, there is uniform weighing or distance-based weighing. The advantages of KNN, it's simple to implement and understand. There's no training phase needed. Predictions are made based on the entire data set. Then disadvantages, computationally expensive with large data sets and sensitive to relevant features and the choice of K. Then the implementation steps include loading data, calculating distances, sorting distances, selecting neighbors, and assigning class. So loading data is basically importing training and test data sets. Then you compute the distances between the test point and all the training points, which I talked about earlier. Sort the distances in ascending order, choose the top k-nearest neighbors, then determine the class based on the majority class among the selected neighbors. Visualization, whereby we use scatter plots to visualize data points and their classifications. Then dimensionality reduction techniques, such as PCA, can help visualize high dimensional data in 2D or 3D. Dimensionality challenges, KNN performance degrades with high dimensional data due to the curse of dimensionality, and feature scaling is effective distance calculations. Next concepts I'd like to be explaining are entropy. So entropy is a measure of the impurity or disorder in a data set. It quantifies the uncertainty in predicting the class of a data point. The formula is also given. Then information gain, the reduction in entropy after data set is split on an attribute. It measures the effectiveness of an attribute in classifying the data. The formula is given below. Then I also like to explain decision trees, a tree-like model used for classification and regression that splits data into subsets based on feature values. Implementation steps of decision trees include calculate entropy for the data set, compute information gain for each attribute, select the attribute with the highest information gain for the split, and then repeat recursively for each subset until stopping criteria are met. For example, maximum depth, minimum samples, and so on. So a decision tree comprises of nodes and edges, whereby the nodes represent the tests on attributes and the edges represent the outcomes of the tests on these attributes. Another concept, and this is the process of removing branch to prevent overfitting. Types of pruning include pruning. You stop tree growth early based on criteria. Then there's post pruning branches after the tree is fully grown based on leaves fully. And then post pruning is done after the tree is fully developed. Then gain ratio, modification of information gain that accounts for the number of branches created by splitting on an attribute. helping to avoid bias towards attributes with many values, and the formula is given. I'd like to pass on to my next colleague to explain the next topic.
Hello everyone, I'm Irene and I'll be taking you through ensemble learning. And this combines many mediocre models in one supermodel. And we have two different types where we have bagging and boosting. And in bagging, we see that it is a parallel tree growing with subsamples, and it is basically random sampling with replacement. This bagging creates different models using different bootstrap training sets and average their predictions, produce the final output of the model. And it also improves prediction accuracy at the expense of interpretability. And for boosting, this is a sequential tree run with weighted samples, and it basically focuses on correcting errors made by the previous models. Then we shall look at a random forest, which is a slightly modified bagging algorithm, basically a collection of decorated decision trees. And we have the pros, which are robust to outliers, works well with nonlinear data, lowers the risk of overfitting, as well as runs efficiently on a large data set. Then for the cons of random forests, we have that it is biased while dealing with categorical variables. It is large training, it isn't suitable for linear methods with a lot of spare features, and the greedy algorithms do not yield the global optimum tree structure. Then we have how we build a random forest. And this is, the first step is we have to first subsample the example. Then for each subsample, we choose attributes at random. Then we randomly pick features in each split and then build the tree only on the random features and with current subsamples. And for the support vector machine, which is the SVM, this gives more weight to correct classification than margin maximization and can detect other outliers as well as ignoring them. It also has the kernel function, which defines the inner products in the transformed space, as well as defining the similarity in the transformed space. Then while evaluating K only requires one addition and one exponentation more than the original dot product does. And for the gamma, this is a hyperparameter that controls the distance of influence of a single training point. For the low values of gamma, this indicates a large similarity radius that results in more points being grouped. And while having high values of gamma, the points need to be very close to each other so as to be considered in the same group. And models in the gamma with models with substantial gamma tend to overfit. Then we have the k-means, where we see that these are the unsupervised learning algorithms used to group similar data points into clusters. And we have the strength and weaknesses, where I find that for the strength, the k-means are simple and easy to understand as well as implementing. Then it is considered a linear algorithm. It is the most popular clustering algorithm. And for the weaknesses, we see that it is only applicable if the mean is defined. It is sensitive to outliers, and it is not suitable for discovering clusters that are not hyperellipsoids. Then we shall finally look at the principal component analysis, which is the PCA. and is used to basically reduce the dimensionality of the data while keeping the information loss at a minimum. It assumes that the values are linearly correlated, and if the correlation isn't linear, meaning the PCA is not efficient, and this PCA performs lossy compression, meaning if information is lost when we discard information which is insignificant, like having insignificant components. And we also have the main applications of the PCA, where we see that there is image compression, facial recognition, data visualization, as well as the processing step for classification, regression, and clustering. Yeah, that was all. Thank you for listening.